Before we get started on homework 5B, I wanted to quickly go over the diagram before we started deriving, mostly because I don't feel like drawing it. It's really big. And so you're going to have to remember this or keep pausing and going back and forth. But let's go over this diagram real quick. And so as you can see here, we have alkene that enters the system along with water. They then react to create alcohol. This alcohol is then gone through a first distillation chamber, in which on the bottom you have a water return line as water is consumed in the reaction. So you're going to continuously need to add water, while you also are going to eventually you're trying to distill, and which means trying to get rid of all of the impurities, and so you want to get rid of any extra water that is out of the system. And so after it's distilled, it goes into another distillation column, in which it is then which then it goes through heteroazeotropic distillation, and again, which is then also has another water recycle line. As what we're trying to do is make sure, again, we get out all of the water inside the tank. And at the bottom of this heteroazeotropic distillation, we have our alcohol line, in which are the alcohol, as this reaction creates two different products. It creates an ether and an alcohol. And so in this third tank, or this third chamber, is where our alcohol drains out of. And our fourth chamber, after it goes through distillation again, is where our ether actually ends up coming out. And for B1, it wants us to write a balanced equation for the production of isopropanol from propylene and water, as well as the dimerization of the isopropanol to disopropyl ether. And so what this is asking us is to draw a generalized equation or show a generalized equation to calculate the production, or it's like a balanced equation, which we can then use in B2 to calculate the, what does it want? To calculate the extent of the reactions and the rates at which they are leaving. And so what I'm going to be doing in B1 real quick is I am going to be writing out the molecular formulas and doing some stoichiometry along with, let me think real quick, along with kind of showing the big picture while hiding all of the smaller pictures inside as, oh, the water return line. We don't really care about how much water is being returned, as we know how much water is added and how much water are in the outlet streams, or we will eventually when we start coding, as what we're doing all right now in B1 is going to be theoretical. So now here, I'm going to transfer you up to the board and we can start deriving. Let's start off by writing the stoichiometry of the reactions along with just the reactions in general. And I don't know if you can see, as I wrote these very small and faint, but in the corner I wrote the chemical formula along with the structure of each molecule that we're going to be using, besides water, because I would hope I could remember that. And so our first reactions, we're going to call this RX1. It is this this alkene plus H2O equals this magnificent alcohol. And now we're going to do this in the actual form. So this is C3. Let's say it's 3 plus 1 plus 2. It's 6. C3H6 plus H2O. Well, I didn't draw it like that this time. And it ends up equaling, so this is going to be again C3. It's going to be H7OH. And so we have the same number of carbons. Let's see, we have, that's 8, and that's 8 hydrogens. All right, and so that is the stoich for the first reaction. So now we can look at the second reaction. The second reaction consists of what we have here. So we're going to have C3H7OH reacts to create our ether, which I'll draw over here real quick, even though I'm not going to draw it in the way, as it's in the way. It looks like, if I can remember correctly, it looks like, let's see, make sure you can see that. Yes, you can. looks like this interesting molecule. And its molecular formula is C6H14O. And as you notice, we also have to add H2O as water is formed throughout this reaction. And so we have 6 carbons and we have 3 carbons. We have 16 hydrogens, we have 8 hydrogens, we have 2 oxygens, we have 1 oxygen. And so we have to add a 2 onto this side to create our stoic, our reaction equations. And one thing you're going to want to remember if you're going through this problem without actual numbers or actual data is that your final flows, or your flows that are leaving your system, are never going to be pure. It is almost or nearly impossible to have a pure flow coming out of a reaction, as a reaction will almost never completely always go through a complete reaction, as there's always intermediates, or, oh, it's not mixed well enough. There's just always these pesky little issues that you're going to come up with. So outside of that, let's work on our ins and our outs. And so if you remember from around 5 minutes ago when I was on the computer describing it for you, we have 2 things that go into this system, as the system being this entire thing of distillation columns. We have our alkene, otherwise known as this lovely little chemical right here, and we also have water. The next thing that we have the only 2 things we have that are leaving our tank, as all of the water should hopefully be recycled, will be our alcohol. I'm not most likely not going to spell it right, that's okay. And our ether. And so from what we have here, what we're going to get is we're going to take our measurements of the flow that is coming out, and we are going to get an array, but we're going to get a composition. And this composition is almost always, or it should be, so I've been told, in the order of volatility. So first we would have our alkene. That's not the name of it. I don't really remember it right now. Then we have our ether. And then third, we have our alcohol. And fourth and not last, we have our extremely volatile, as you know, water. And so what we're going to do is we have the numbers here. So we have this number, we have this number, and we also have the array of here, and the array of here. And so what we can do is we can measure, or not measure, as we know the amount of alkene that comes in and the amount of water that comes in, and we know the amount in which they are going to react, because we know the stoichiometry, and so we can start dividing and going through like, hey, if we have 95 moles per second that comes in, we're going to say, if we have 95 moles, that gives us eventually, if we have excess water, which we should, it gives us 95 moles of our alcohol, which should then go through and give us, depending on how much is reacted, we'll divide by 2. We're going to get around 47 moles of this ether. But if we are trying to designate something more than the other, we can start dividing or start figuring out, oh, if this reaction did not go all the way through, or we are trying to get this specific answer and it doesn't go through, we can see, oh, we actually have, I don't know, 5% water in there somehow, along with 0.1% alkene, which will eventually prove, or as I will show you soon, the reaction, or not the reaction, but the amount of your reaction has gone to completion, along with the different values that go along within this column system. So now I'm going to get onto Colaboratory and code out this problem, which is, again, as you saw earlier, has actually given us some values for us to calculate. So now that we've kind of that we've gone through and written out kind of the big picture, what comes in and what goes out, now we can kind of code this out and figure out the more distinct and exact numbers of what was given. So we've gone over this picture, but let's go over B2 again. So given that pure propylene, or our alkene, and water feed flow rates of 195 moles per second respectively, and then they have distinct mole fractions, which are in the order of propylene, diisopropyl ether, isopropanol, and water, and then it's the same order for the ether and alcohol fractions of their streams, and this is in order of reactivity. We want to calculate the molar flow rates of the ether and the alcohol product streams, as well as the extent of the two reactions. And so what I've written down here is just kind of as a reminder what we went through. So this is reaction 2. No, this is reaction 1 and reaction 2. They're also stoichiometrically correct, along with the order of which we're going to use. And then these are what we want to calculate. So let's write, before I start going through that, let's get what we have up here. This is something my professor has created, and what this is a lot of very useful different equations, or like, oh gosh, I'm trying to think what to call them, useful functions that we can use. It has the range, composition, comp, range directory, D2NT, and then here we've imported numpy and scipy optimize. So we're going to do rx1 underscore stoich, and that is going to equal np.array. Let's see. So we have our alkene first, and so if it's going to be consumed, we're going to have -1, right? And if we're going to do, so it's going to be -1 alkene, and then it's going to be ether. Ether is not involved in this part. And then after ether is the alcohol, and we're going to create 1 mole, and then 1 mole of the water that is then involved in that reaction. And then the next reaction, rx2 stoich, that equals np.array, and we are going to be taking 2 moles of our alcohol to create a mole of the ether. Okay, so we're not using any of the alkene, so it's going to be 0, and then the ether, we're going to create 1 mole. Then we're going to use 2 moles of the alcohol, and we're going to actually be creating a mole of water. Right? Yes. So now that we have this, let's go through what we were given. So first, let's do our alkene feed. So our alkene feed, so we're going to call this prop F equals 100 or 105. Propylene is given 100 moles per second. I don't like, it always does that. And then that's a feed. Now our, then prop X. Let's see, I'm trying to figure out what I want to do first. So we could either do the array of the amount that's coming in. Actually, we're going to do that. So our alkene, that's the wrong thing, prop X, right? And so what we have here is we're going to create an array for what that composition is. And we are assuming that the composition is pure. So we're going to have, let's see, it's alkene, so it's going to be 1, and then 0. And we're going to do the same with our water feed, as we are, as our water feed, which is 95. So we're going to do water F equals 95, and then along with the water X, let's call this Y. I don't like having proof of this as X. and that is going to equal 0, 0, 0, 1. Now we can do our exit feeds as we want to. So we want to calculate the molar flow rates as well as the extent of the reactions, and we are given the external or the leaving amount of the leading mole fractions. So we're going to do, keep it in the wrong thing. I'm going to put that here. So we're going to do, what should we call this? We're going to call this alcohol P along with ether P. And we're also going to separate these again as what we want to calculate are the rates. And so we're going to make a guesstimation on those rates depending on the, let's see, feed. Let's do R, just designate rate. And then we'll use X as the amount of, as our array of what's in it. And so for the mole fractions, let's do all X, and that equals NP dot array of 0.001 0.9 let's see. Oh, so what I'm actually, I'm gonna have to, this is in the wrong, let's see, I'm just gonna Control C, ether X. And so what I'm doing is right here, and it says in the ether and alcohol. So this is going to be, this is the ether amount actually. So it is then 0.09 and then 0.0, it's 0.01. And if you notice something, there's a small typo in this, as we want all of our mole fractions to equal 1. And if you notice, this right here equals 1. But then there's a very small typo here. Like this might have to be, we can make this 0.099. I'm going to leave it as is, as we are given, like, there's answers that are similar. I won't want to affect the answers. Like I can change it at the end, which I think I'll do, just to show you how that'll affect the problem, which it should be very minimal. And now we can do the alcohol. So also 0.01, but then 0.1, 0.94, and then 0.049. So you see this equals 1. Right? So we have 9.4 plus that is 9 is 0.05, add that is 0.99, then add right here, you get 1. And so we're going to guess that the alcohol rate is going, we're going to say this is 90, and that the ether is 10. And these are variables that we're going to be calculating for, so this is actually an unknown / a guess. Let's see what else. Are we given anything else? All right, so now we have our alcohol stoichiometry. We have our stoichiometry. We have our alcohol guess rate along with the alcohol composition. We have our ether guess rate along with the composition. We have our propylene and our water flow rates along with the composition inside. So now we are going to create a function in which that it's going to be a vector. It's going to solve for 4 things. It's going to solve for the flow rates and the extent of reaction. And we're going to be using the stoichiometry along with the water and alcohol rates and see and combine and add those and hopefully get to 0. Or no, we're not going to hopefully get to 0. We're going to create our equation, and we're going to use root solver to get that equation to 0, which will then give us our 4 variables. So we're going to what should we define this as? We're going to define this as MBS. We're going to call that a vector. And let's see. So we're solving for flow rates, so ether and alcohol. Let's see, what order did it come in here? So it came in order of ether and then alcohol, so we'll do that in this. And then we also want their reaction 1, reaction 2. And so another guess we're going to make is we're going to make EXTR1 and EXTR2. And we're going to assume that the extent of reaction of reaction 1 that creates the alkene not the alkene, that creates the alcohol. As you see here, we get 0.94. So we're going to assume this is around 90%, 90% completion. And for 2, we're going to assume it's 10. And this is just easier as, again, this is another unknown / guess. And these are what we're going to be calculating for. And so we're going to be doing, what word did I say again? It was ether and then alcohol. So we have ether PR, comma, alcohol, PR, product rate, and then we have EXTR1, EXTR2. And let me go save that again, just so we don't get an issue when it's undefined. And these are all going to equal our vector. So this is just unpacking. So now we need to start multiplying our values together and then adding up separately. So we get the compositions that will eventually add up to 1. So now what you want to think about this as in terms of our box. We're going to have a feed, we're going to have our reactions, and we're going to have our product. And so in our feed, what are we adding? We are adding our, what do we call this? Our prop, F, and then we want to multiply that by the composition, times comp, times prop Y. Plus, now we're going to do the exact same thing with the water. So water F times water X. For the reactions, we are going to do extent of reaction, so EXTR1 times the stoichiometry of reaction 1. So we're going to do RX1 stoich. Same thing with the next one, so it's going to be EXTR2 times RX2 stoich. And for the products, it's going to be our alcohol and the alcohol and the ether. So it's going to be alcohol times out. No, never mind. I'm just wondering if the order I'm multiplying this matters, but I really don't think it should. But alas, we will find out. Alcohol X plus ether PR product rate times ether X. And now we want to return, we want to do feed plus reactions minus product. And theoretically, we want this to equal 0, right? As if it equals 0, that means everything we calculated is correct. And to do that, we need to take the root. So we're going to do root of the function, which is MBS, which is then, let me copy this. And I believe that should be it. This might need to be in brackets, but we will find out. Yeah, so this is just going to need to be in that, I believe. Let's see if that works. So it says function object is not subscriptable. which means well, it obviously means I made a mistake somewhere, but let's see, 90. Let's see, so it says object function is not subscriptable. I'm trying to figure out why it would. So this is the function. Do I need to, maybe I need to apply initial guesses, but let's think. So as you see, we're still getting this error, but I found out because I, not paying attention, didn't do this and make that an array, because that just makes it a single dimension, which screws it up, and we end up getting this fantabulous, interesting thing. So you're going to do .x, which will grab the x values, which means the ether product rate will be about 9 moles, 9.27. The alcohol product rate will be around 85.8 moles per second. And then the extent of reaction 1 is 99.9, and the extent of reaction 2 equals 9.2. And this is just based off of our guesses here. And so let's say, screw it. We think the alcohol is actually closer to 100, and we think the ether we're going to keep at 5. And so let's look at that. It changed this. I think it changed it very minorly, but you can still see it makes a little bit of a difference just based on your guess. And what this does is we have actually calculated the molar flow rates, which are the first two x values, along with the extent of the two reactions, which we calculated here and here. And so what this means is we can have a guess, and so we don't even really need to calculate these values, as if you just make a guesstimation, you can get a very reasonable and accurate value just by plugging the numbers in. And so now what we're going to be doing is, in homework 5, is the brief synopsis, is we're going to be retrofitting these values here and making a dictionary so we can call on them more than once, as homework 5 is a whole different beast than what homework 5 is. Homework 5C is a whole different beast than homework 5B. But yeah, that is the end of homework 5B and the 2, as this is the coding portion.